2. Where n is that binary sequence that I just said a second ago. It's a 1 if it's a 1 if a flip occurs, and a 0 if a flip does not occur. So x plus 0 mod 2 is just x. So if this noise is 0, no flip occurs. X plus 1 mod 2, that's like XORing with 1, and that always flips the bit. So this is like additive noise, and this calculation is basically the entropy of that additive noise. Okay, so that's h of y given x. Now, mutual information. Is equal to h of y minus little h of p. Now, we could calculate h of y, and then maximize it explicitly with respect to, we could maximize it explicitly with respect to p of x, the input distribution, to find the capacity. But let's see if we can think of something more clever. So h of y is in the set sy, which is binary. So if sy is binary, what's the maximum entropy I can have on a binary set? 1. So it seems like this has to be less than or equal to 1 minus h of p. So all we need to do is we need to figure out whether this is achievable, whether or not there does exist. Because remember, this term, the h of p term, doesn't depend at all on x, on the distribution of x, because the distribution of x came out. So h of p, that's true. This term is the same regardless of the input distribution. So all we need to do is find an input distribution such that h of y has entropy 1. So when does h of y achieve its maximum entropy? When would a binary random variable achieve the maximum entropy of 1 bit?
Equiprobable.
If it's equiprobable. So basically we need probability y equals 0 equals probability y equals 1, which is 1/2. So looking at this, if I want probability 1/2, 1/2, what should the p of x be just intuitively? So I want p of y, 1/2, 1/2. What should I start with on p of x? Should be 1/2, 1/2, right? So you can sort of think of it as following each path. So if you like, 1/2 times 1 minus p goes this way, 1/2 times p goes this way, they add together and you end up with 1/2. 1/2 times p goes this way, 1/2 times 1 minus p goes this way, and you end up with 1/2. So therefore, you can show this explicitly, but if p of x equals 0 equals p of x equals 1 equals 1/2, that will lead to this, which will lead to that. So therefore, the capacity, the capacity must be less than or equal to that, because that's the maximum that h of y can be. And if I choose an input distribution, an equiprobable input distribution, this is achievable. So therefore, capacity is 1 minus h of p. So I'll leave it to you to show that this leads to that, and then that leads to that, and therefore that's achievable. So this is actually much less than, this capacity is much, much smaller than in general, it's much, much smaller than the erasure capacity for the same probability. So for instance, if p is equal to 0.11, do you have a question? Okay.
I'm having difficulty with seeing the board, that's why.
Okay. If p is equal to 0.11, you would need a calculator to figure this out. But if P is equal to 0.11, little h of P is approximately 0.5. And what that means is the capacity of this channel would be about 0.5. On the other hand, if PE, the erasure probability in the binary erasure channel, is equal to 0.11, the capacity of that channel is approximately 0.89, much, much higher. So noisy channels like this tend to be much harsher than, for example, the erasure channel that allows certain bits to pass without any errors at all. What do you, for what value of P do you think the smallest capacity possible is achieved? What's the worst value of P? The worst value of P, it turns out, is 1/2. So h of P, remember this is just the binary entropy function, so this is the entropy of a binary random variable with probability of 1 equal to P. So if I have a binary random variable with probability of 1 equal to 1/2, that's maximum entropy, so therefore this would equal 1, and the capacity of such a channel would equal 0. What does that mean? Basically, if the crossover probability is 1/2, the capacity is 0, so therefore no information can be sent. In particular, the interpretation of mutual information being equal to 0, we mentioned this last time. If mutual information is equal to 0, then x and y are independent. So basically, if your noise is flipping half the bits, then basically what you're doing is you're taking the input and applying a sequence to it that makes the output independent from the input. So no information can pass. Some people think that's weird because it might seem like larger values of P are worse. So what happens, for example, if P is equal to 1? Every bit is flipped.
But then it's awesome, because you just switch all the bits.
Exactly. So if every bit is flipped, then you in fact have perfect transmission, because all that means is at the other end you flip every bit back, and then every bit is received without any error. What is the capacity in that case? If P is equal to 1.
1.
It's equal to 1, because what if I substitute in P is equal to 1 over here, I get 1 times log 1, which is 0, plus 0 times log 1 over 0, which we've defined as 0. So therefore h of P is 0 and capacity is 1. In fact, if I plot this capacity,
it's a parabola, I think.
it's not precisely a parabola, but it looks parabolic, so it does look like this. But it's not produced by a quadratic equation, exactly. So it has a minimum equal to 0, 1/2, and at both 0 and 1, it's equal to its maximum, which is 1. But yeah, it is symmetric. It appears parabolic.
Isn't it the other way around?
No, this is capacity, not entropy.
Oh.
Entropy. And so h of P looks like this. That's h of P, and this is capacity. Alrighty. So today's job is to set up the definitions we need to prove this. What we're working towards is a proof of the statement that capacity is the highest achievable rate at which you can communicate reliably.